In this video, we are going to talk about impulse function and convolution. They're not related really. These are just the last two topics to finish this Laplace transform subject. Okay, so first, impulse function. Basically, impulse function comes from the need to find a function. So the idea is to define a function which we are going to denote by delta t, so that its Laplace transform is equal to the constant function 1. The functions we have considered so far have Laplace transforms as either a rational function or a rational times an exponential function. So none of them have this property that their Laplace transform is equal to 1. So this is going to be a new function. But as it turns out, it is not easy. So first, we define a sequence of functions for n, taking the value of natural numbers 1, 2, 3, and so forth, we define the function f sub n of t to be the value n if t is between 0 and 1 over n, and 0 otherwise. So this is like okay, maybe just a bit more careful. But on the t-axis, let's take one longer. So f sub 1 f sub 1 is f sub 1 is equal to 1 for t between 0 and 1. And 0 otherwise. Okay, so 0 otherwise. Then f sub 2 is, oops, okay, it's not a good idea. One moment. Okay, this is the t-axis. F sub 2, on the other hand, is equal to 2 from 0 to 1/2. And 0 otherwise. and f sub 3 is equal to 3 for t between 0 and 1/3, and 0 otherwise. And f sub 4 is equal to 4 for t between 0 and 1/4, and 0 otherwise. So you see the value, the maximum value of the function increases, but the interval on which the function, this is not 1/4, I'm sorry, this is 1/4. But the interval on which the function takes this maximum value gets smaller and smaller. Okay, so these functions have the property that when you take the integral of these functions on the whole interval from on the whole real line, the function is not 0 only from 0 to 1/n, and the value of the function in this interval is just n. So the value of this integral is always going to be 1. So in other words, for f1, the integral is this area, and this area is 1. For f sub 2, the integral is this area, and it is again 1. For f sub 3, it is this area, and it is again 1. So the area under the graph of the function is always, for every n, it is equal to 1. And now we consider taking n getting larger and larger. So we define our function delta of t to be the limit as n goes to infinity of f sub n. So this is like, since the interval is getting smaller and smaller and getting close to 0, so delta is like at 0, 0 taking a value which goes to infinity, okay, as n goes to infinity, but it is only at 0. So the interval is getting smaller and smaller. So 1/4, 1/8, 1/16, 1/32, and so on. So the interval is getting smaller, and in the limit, it becomes just 1 point, just 0, and the value goes to infinity. So this is a weird looking function. It is, I'm sorry, it is 0, this limiting function, it is 0 for all t except 0, right? Because I'm taking the limit as n goes to infinity, so the function is, you see f sub n is 0 except the interval from, so f sub n of t is 0 if t is not in the interval, if t is not in the interval 0, 1/n. And as n goes to infinity, this interval tends to just 1 point. So in the limit, the function delta is 0 if t is not 0. Okay, on the other hand, since all functions have integral equal to 1 for all n, in a way, the integral of this function delta t is also 1. Of course, this is not possible for any function. If the function is 0 everywhere except just one point, we expect its integral to be 0, not 1. So this is not possible for a function. And in fact, this function we call delta is not a function. Delta t is not really a function. It is what we called a generalized function. So the theory of this can be made more rigorous, but we don't need to go into that here. So at this point, consider delta t formally as formally with the property that when you take its Laplace transform, it is constant 1. Now, why? Okay, how do we get this? Why its Laplace transform is 1? Okay, so explanation of why the Laplace transform of this function is 1. Okay, since we define delta t to be the limit of these functions f sub n, let's figure out the Laplace transform of f sub n. Now remember, what is f sub n? N if t is between 0 and 1 over n, and 0 otherwise. So I'm going to write f sub n using unit step function. So we start with n plus the break comes at 1 over n. So we use the unit step function at 1 over n. And then we take the function for t larger than n, which larger than 1 over n, which is 0, minus the value of the function for t less than 1 over n, which is n. So it is n minus n times unit step function at 1 over n, or n times 1 minus unit step function at 1 over n. Okay, so what is the Laplace transform? N is just constant. Laplace transform of 1 is 1 over s minus Laplace transform of unit step function at 1 over n, e to the minus 1 over n times s. So e to the minus s over n divided by s. And now we take the Laplace transform of delta t is just the limit as n goes to infinity of Laplace transform of the function f sub n. So we take the limit as n goes to infinity of n times 1 minus e to the minus s over n divided by s. Now, how do we take this limit? First, I'm going to make a change of variables. So let x be equal to 1 over n. And then, as n goes to infinity, x goes to 0. So this limit I can write in terms of x. So instead of n, I write x, and x goes to 0. N is equal to 1 over x. 1 minus e to the minus s times 1 over n, but 1 over n is x over s. So I can write this as 1 minus e to the minus sx over Sx. So this limit is on x, and as x goes to 0, e to the 0 is 1, so the numerator goes to 0, denominator goes to 0, so this limit is 0 over 0 undetermined type. So we can use L'Hopital's rule. This limit is equal to, I take the derivative of the numerator, derivative of 1 is 0, minus derivative of e to the minus sx, e to the minus sx times derivative of minus sx, which is minus s, divided by derivative of sx is just s. So if you simplify, we have e to the minus sx. So as x goes to 0, e to the 0, the limit is 1. So that means Laplace transform of this function delta t is equal to 1. Okay, now, as I said, consider this as a formal function, generalized function, something, think about it just as some notation. This notation, delta t, its Laplace transform is equal to 1. Of course, it has a physical application. It corresponds to giving an impulse force, so only for one moment. This impulse function is 0 everywhere except t equals 0. So consider this as a time, an instant. At the instant t equals 0, we give an impulse to a physical system. Okay, so that's why it's called the impulse function. So instead of time 0, of course, if we shift it by c, positive c, we get delta t minus c, which is impulse at time t equals c. So at the time t equals c, we give an impulse function, impulse force. We give a momentary force just for that instant to a system. Okay, then what is the Laplace transform of this shift? The shift, since the function is not 0 only at the point t minus c, you can consider this as multiplied by unit step function at c. For t equals c, remember the unit step function is 1. So for t equals c, we have delta. And otherwise, since delta is 0, this product is also 0. So this transform is e to the minus cs times Laplace transform of delta, but that's 1. So Laplace transform of, if you shift it by c, it is e to the minus cs. So if you shift it by 0, the original delta t you can consider as delta t minus c for c equals 0, and when c equals 0, e to the 0, it's 1. So it is consistent with Laplace transform of delta t. So how do we use it in differential equations? As before, we take the Laplace transform and use this formula for Laplace transform of the impulse function. So, for example, let's solve the initial value problem. y double prime minus 9 times y equal to 15 times delta t minus 3 pi plus 12 times delta of t minus 6 pi, and initial conditions y0 and y prime 0 to be 0. And also find the value of the solution function at t equals 13 pi over 2. Okay, so to solve this, we apply Laplace transform to both sides. So Laplace transform of y double prime minus 9y equal to Laplace transform of 15 delta t minus 3 pi plus 12 delta t minus 6 pi. All right, so what is the Laplace transform of y double prime? Let's use the formula. Minus y prime 0 minus s times y0 or s times y0 and plus s squared times Laplace transform of y minus 9 times Laplace transform of y equal to 15 times Laplace transform of delta shifted by 3 pi, so e to the minus 3 pi s plus 12 times Laplace transform of delta shifted by 6 pi e to the minus 6 pi s. So on the left side, y prime 0 is 0, y0 is 0. So we have s squared minus 9 times Laplace transform of y. So Laplace transform, capital Y of s, 15, it's constant, so I write it in front, e to the minus 3 pi s over, oops, s squared minus 9 plus 9. Where's my example? I'm sorry, where's my example? I'm sorry, in the example, it should be plus 9. I didn't write this right. Okay, over, so this is s squared plus 9. S squared plus 9 plus 12 e to the minus 6 pi s over s squared plus 9. Now to find the Laplace inverse, we need to find first Laplace inverse of 1 over s squared plus 9. Since we have 9, 9 is the square of 3, we need 3 in the numerator. If we have 3 in the numerator, then this is sine of 3t, right? So our solution, which is the inverse Laplace of capital Y. So I need 3 in the numerator. I'm going to write, so Laplace inverse, I'm going to write 15 as 3 times 5. So 5 e to the minus 3 pi s, 3 over s squared plus 9. Plus, and 12 is 3 times 4. So this is 4 e to the minus 6 pi s, 3 over s squared plus 9. So we have 5. Since we have exponential function, it means we need the unit step function at 3 pi. So inverse Laplace of 3 over s squared plus 9 is sine 3t. But since we have the unit step function at 3 pi, instead of t, we take t minus 3 pi. And plus 4 times, since we have e to the minus 6 pi s, we have unit step function at 6 pi. And in sine 3t, instead of t, we take t minus 6 pi. So this is the solution. Okay, what I'm going to do now, you don't have to, when you're solving an example, but in order to understand better what all these step functions mean, first of all, since we have the sine function and t minus 3 pi and 6 pi, we can simplify those functions. So let me do that first. So sine of 3, t minus 3 pi. So this is sine of 3t minus 9 pi, right? So using the addition formula for sine, this is sine 3t cosine 9 pi minus cosine 3t sine 9 pi. Now sine of 9 pi is of course 0 and cosine of 9 pi is minus 1. So this is minus sine 3t. And the other one, sine of 3t minus 6 pi. This is sine of 3t minus 18 pi. So using again addition formula for sine, sine of 3t cosine of 18 pi minus cosine of 3t sine of 18 pi. Sine of 18 pi is of course 0 again, and cosine of 18 pi is now 1. So this is sine of 3t. So basically, our solution is 5u3 pi times, sorry, this is a minus sign, right? So minus 5u3 pi sine 3t plus 4u6 pi, again, sine 3t. Now, what does it mean? Remember the definition of the unit step function. So this means, first of all, the function is 0 if t is less than 3 pi. Because if t is less than 3 pi, it is also less than 6 pi. So both u3 pi and u6 pi are 0. Now, if t is between 3 pi and 6 pi, u3 pi is going to be 1, but u6 pi is going to be 0. So minus 5 sine 3t if t is between 3 pi and 6 pi. And if t is greater than 6 pi, both unit step functions are 1. So minus 5 plus 4, I have minus sine 3t if t is greater than or equal to 6 pi. And finally, we are asked to compute y of what? 13 pi over 2. 13 pi over 2 is 12 pi over 2 is 6 pi plus pi over 2. So it is greater than 6 pi. So that means we use minus sine 3t. So it is minus sine 3, 6 pi plus pi over 2. 3 times 6 pi, remember the period of sine function. So this is 18 pi plus 3 pi over 2. Remember the period of sine function is 2 pi. So 18 pi is 9 times 2 pi. That means this is the same as minus sine 3 pi over 2, and sine 3 pi over 2 is minus 1. So the answer is 1. Okay, now to finish off this Laplace transform business, we have one more topic to consider. It is the convolution. Now, the idea of convolution comes from this. Now, if we know that Laplace transform of some function f is capital F of s, and Laplace transform of g of t is capital G of s, can we find the Laplace inverse of the product of the two functions? In other words, which function has Laplace transform, which is the product of the function capital F and capital G? And the answer to that is the convolution. We define the convolution of F and G, denoted by F star G, and we define it by, so it is a function. F star G is a function of t. We define it by means of an integral. We take the integral from 0 to t, and we need a variable for the integration. You can use any letter. In the definition, usually we use the letter tau because it's the Greek letter for t, but I'm going to use u. So inside the integral, you write f of t minus u and g of u du. The order of f and g is not important, so it's the same as f of u, g of t minus u du. It's the same thing. You can try making this substitution, change t minus u to a new variable, say v. You see, you get this integral. Okay, so the order of f and g is not important. G convolution f t. It doesn't matter. Okay. To see, so the variable of integration is u. We keep t fixed. We are trying to define a new function f star g, and its value at fixed t. Once you fix the t, you take the integral with respect to u. Okay. To see how this works, let's do an example. What would be the convolution of two exponential functions, for example? If f of t is, say, e to the 2t, and g of t, let's say, e to the minus 5t. What is the convolution? We take the integral from 0 to t. We write, okay, let's write this down. T minus u, g of u, du. So 0 to t. F of t minus u. In f, instead of t, we write t minus u. And in g, instead of t, we write u. And we integrate with respect to u. So 2 times t minus u, e to the 2t times e to the minus 2u, e to the minus 5u. The integral is with respect to u. So e to the 2t is constant. I can take it out of the integral. e to the minus 2u, e to the minus 5u is e to the minus 7u. Okay, so if I take the ni derivative of e to the minus 7u with respect to u, e to the minus 7u divided by minus 7. And I evaluate this for u from 0 to t. To t, not u, I'm sorry, to t. So if I put u equals t, I have e to the minus 7t over minus 7, minus, if I put u equals 0, e to the 0 is 1 over minus 7. So I have minus e to the minus 5t over minus 7 plus e to the 2t over minus 7, or over 7, not minus. Wait, this is, what am I doing? So e to the 2t minus e to the minus 5t divided by 7. As another example, let's take f to be unit step function at 2 and g to be unit step function at 5. Now, what is f convolution g? Integral from 0 to t, f of t minus u, g of u, du. Okay, so function f is, so f of t minus u. This is going to be 0 if t minus u is less than 2, and 1 if t minus u is greater than or equal to 2. And g of u is 0 if u is less than 5, and 1 if u is greater than or equal to 5. So I can rewrite f as 0 if u is greater than t minus 2, and 1 if u is less than or equal to t minus 2. Okay, so when either f or g is 0, the integral is going to be 0. So we need to find the interval when both f and g are equal to 1. Of course, that depends on the value of t. Now, if this point, t minus 2, is greater than or equal to 5, if t minus 2 is greater than or equal to 5, then, okay, let's see. So here is t, here is t minus 2, and here is somewhere here is 5. Okay, so in the integral from, let me see, I should have said, let's take the case, this is easier, less than 5. If t minus 2 is less than 5, then 5 is either somewhere here or it may be over there, larger than t even. But when you break up your integral from 0 to t, from 0 to t minus 2, from 0 to t minus 2, since 5 is up here, g of u is going to be 0. Okay? And From t minus 2 onwards, this is the u axis, by the way, the value of u. When u is greater than t minus 2, f is going to be 0. So if t minus 2 is less than 5, then the integral is going to be 0. Okay, now in the other case, if t minus 2 is greater than or equal to 5, then, so here is t, this is the u-axis, t minus 2, and somewhere here is 5. The integral up to 5, g of u is 0. And after t minus 2, f is 0. So we only have this interval from 5 to t minus 2. So this integral is going to be the integral from 5 to t minus 2. In this interval, both f and g of u is 1, and f of t minus u is also 1. So we have just 1 times du. So we have t minus 7 minus 5. So we have t minus 2. I'm sorry, not 7. Whoops. So t minus 2 minus 5. So this is t minus 7. And if 5 is equal to t minus 2, if 5 and t minus 2 are both the same number, then the result is 0. But t minus 7, t minus 2 equal to 5 means t equals 7. So if t minus 2 equals 5, then t equals 7. And either as the integral or with the formula t minus 7, and convolution is 0. So the convolution function in this case is 0 if t less than 7, and t minus 7 if t is greater than or equal to 7, right? It is 0 if, it is 0 if t minus 2 is less than 5. So when t is less than 7, it is 0, and otherwise it is t minus 7. Okay. So we can also write this as t minus 7 times u7t. Okay. Now, the main thing, why do we consider this convolution thing? So the main thing about the convolution is that the theorem, when you take the Laplace transform of f convolution g, it is the Laplace transform of f times Laplace transform of g. Okay, so proof, I'm not going to do it here. Proof is in the lecture notes. I'm going to share in auto class. So if you're interested in the proof, It is not hard, but you should be able to think a little bit abstractly about double integrals, changing the order of a double integral, and so on. But it's not hard. You can check you can see the lecture notes. I want to show you examples. We can use this to find the inverse Laplace of something like s squared plus 5s plus 4. Now, remember how we used to do this? We try to factor it out, and in here we can factor out s squared plus 5s plus 4 as s plus 1 times s plus 4. And we use partial fractions to write this as the sum of two fractions, one with the denominator s plus 1 and the other with denominator s plus 4. But now with convolution, we can consider this as the product of 1 over s plus 1 and 1 over s plus 4. So by this theorem, the inverse Laplace is going to be the inverse Laplace of 1 over s plus 1, convolution inverse Laplace of 1 over s plus 4. Okay, what is the inverse Laplace of 1 over s plus 1? It is e to the minus t. Convolution, e to the minus 4t, right? 1 over s plus 4 is the Laplace of e to the minus 4t. So the Laplace inverse is going to be the convolution of e to the minus t and e to the minus 4t. So what is the convolution? Integral from 0 to t, e to the minus t minus u, e to the minus 4u du. So e to the minus t times the integral e to the plus u, e to the minus 3u du. So e to the minus 3u over minus 3, u from 0 to t. So e to the minus 3t over minus 3 minus e to the 0 is 1 over minus 3. So e to the minus t minus e to the minus 4t over minus 3. Over 3, I'm sorry. I keep doing the same mistake. Okay. And you can check this answer by finding the Laplace inverse. Finding the Laplace inverse. With the other method, with our previous method using partial fractions. So now, instead of partial fractions, if you want, you can use convolution, whichever comes easier for you. Let me do another example. Suppose that yt is the solution of the initial value problem y double prime plus 5 times y prime plus 4 times y equal to g of t, some function g, which is not given. With initial conditions, y0 and y prime 0 equals 0. Express y in terms of the function g. So this is the question. And the answer is taking Laplace transform of both sides. Since the initial conditions are 0, on the left side, I have s squared plus 5s plus 4 times Laplace transform of y. So Laplace transform of y is 1 over s squared plus 5s plus 4 times Laplace transform of g. And we figured out the Laplace inverse in the previous example. Laplace inverse of 1 over s squared plus 5s plus 4, it was e to the minus, what was it? E to the minus t. So this is the Laplace of e to the minus t minus e to the minus 4t divided by 3. So this one from previous example. For example 1 above. I hope this is clear. This is the example we just did. Example 1 above. Okay. So we have the product of Laplace transforms of two functions. We know that this is the Laplace transform of one function, convolution the other. So my function y of t is e to the minus t minus e to the minus 4t over 3 convolution g. So this is the integral from 0 to t, e to the minus t minus u minus e to the minus 4t minus u over 3 times g of u du. Of course, since I don't know what g is, I cannot figure out this integral. But the problem asked me to express my function y in terms of g, and that's what we did. In this expression, we have the function g. All right, so this basically finishes, this is the end of the subject on Laplace transform. And ordinary differential equations, in fact. This is all we are going to consider in the subject of ordinary differential equations. Okay, if you look at the schedule, you see that we have 2 more weeks to cover. We have 2 more weeks to cover. And that involves about partial differential equations, PDEs. Okay, so my next videos, okay, for the lectures, 2 more weeks, it means 4 more lectures, but this is lecture 24, so we have lecture 25, 26, 27, 28. I think I'm only going to do 2, maybe 3. I have to 25 and 26, and maybe I can do a wrap up in lecture 27. But remember, the lectures come in, parts. So don't consider each lecture as just one video. I will try to break it up into, small pieces so that you can understand better what we do about partial differential equations. But at this point, this is the end of ordinary differential equations. Okay, so I will talk to you later in my next video about PDEs.